SwayamPrabha. Digital India. Educated India.
So welcome to lecture number 19 of the Statistical Thermodynamics course. So in this particular lecture, we are first going to look at Pauli's exclusion principle. It is Pauli's exclusion principle. Okay. So Pauli's exclusion principle, as the name suggests, was developed by the German physicist Wolfgang Pauli, who was also known as the conscience of physics. Okay. The principle directly follows from the symmetry requirements of the wave functions that we just covered in the previous lecture. Now let us consider, to rationalize this, let us consider a system of independent particles. Okay, all right, whose wave functions okay, is like multiplicative. It's a product of the component of wave functions. Product of component wave function. All right. So for us, say, let's take a two-particle system. All right, two-particle system here. In this two-particle system, let's write the total wave function R1, R2 is given as, okay, say, psi I1, j2. Okay, it's a product of the two wave functions. So psi I, okay, or psi I rk is basically, it designates that particle k is in quantum state I. Right. Unfortunately, this particular thing suggests that the wave function is neither symmetric nor anti-symmetric with respect to the exchange of two particles. So if we exchange two particles, we cannot say whether this wave function is symmetric or anti-symmetric. Now, if I, on the contrary, write it like R1, R2 is equal to psi I1, psi j2 plus minus psi I2, psi j1. All right. If I write it like that, this is clearly either symmetric. This is clearly either symmetric or anti-symmetric, depending on whether this sign is positive or negative. Whether this is positive, or negative, right? So clearly, so that is the symmetric or the anti-symmetric wave function. So because the Schrodinger's wave equation is a linear partial differential equation, since the Schrodinger wave equation is a linear PDE or partial differential equation. Okay, the sum of its solutions are also valid. Sum of its solutions also valid solutions. Okay? So that means this is therefore clearly a solution. This particular thing that we have written is clearly a solution of the Schrodinger's wave equation. Okay. So this equation therefore satisfies the parent wave equation plus any symmetry requirement that you might have. Okay. Now let us assume now if two particles have Okay, anti-symmetric wave function. Anti-symmetric wave function. Okay, wave function. And we attempt to put them in the same quantum state. And we try to put them in the same quantum state. Quantum state, which essentially means that psi I will be equal to psi j. Okay, so therefore the equation that we wrote previously, which is this equation, will now become psi r1 comma r2 is equal to psi I r1 into psi I r2 minus psi I r1 into psi I. So this is psi I r2 into psi I r1. Okay. That is equal to 0, right? So why we have the negative sign? Because this is anti-symmetric. So that's the reason. So this essentially translates to what? That means otherwise the contemplated solution. So the solution that two particles have the same quantum state. Okay? Same quantum state, okay, has zero probability, okay, of occurrence. Hence is an impossible solution. Hence is an impossible solution. So this important result is called the Pauli's exclusion principle. This is called Pauli's exclusion principle. Okay, or in other words, two like particles with anti-symmetric wave functions cannot have the same quantum state. In other words, two particles, okay, which has got the anti-symmetric, or two like particles, say, like particles, okay, with anti-symmetric wave function, okay, cannot the same quantum state. Okay, this you read in your probably your 12th standard and your undergraduate. So this is essentially what it means. So such particles, for example, electrons are such particles, right? It's because they have anti-symmetric wave function, therefore they cannot have the same quantum state. Okay. And we will see how the spin and other quantum numbers comes naturally out of this. So for example, so two particles, but they must be belonging to the same multi-particle system. That means two electrons, just an example, two electrons in separate atoms. Separate atoms, do not classify, right? It's separate atoms can be in same quantum state. Can be in same quantum state. Okay, but if these two atoms form a molecule, okay, then the two electrons must be in different quantum states. Got it? So this is what is called, okay, this is the rationale. So the two electrons must be belonging to the same multi-particle system, right? If they belong to two different atoms which are not linked with each other, then they can have the same quantum state. But when they form the molecule, they become a part of the same multi-particle system. As a result of that, they have to obey the Pauli's exclusion principle. So in general, we can write it as a wave function is written as R plus minus 1. These are the number of ways in which the particles can be exchanged, which we covered in the previous lecture. And this is psi R1, psi 1 R1, psi 2 R2. Yeah. So this is for independent particles, okay, where the positive and the negative signs are invoked respectively for the symmetric and anti-symmetric wave functions. Okay, so it's taken over all. This is taken over all possible operators, by the way. Okay, so hence the overall wave function can vanish only if the individual wave functions are anti-symmetric. So that is the reasoning. Okay, we would be able to use the Pauli's exclusion principle to build up the periodic table, for example. As I said, chemistry is a lot of quantum mechanics. In fact, quantum mechanics that we talk about. Okay, so just a brief insight about the correspondence principle right now. So the correspondence principle was proposed by Niels Bohr. So as we found that the laws of classical physics have been found to work in the macroscopic domain, so Bohr argued that satisfactory quantum theory must approach its classical counterpart when applied to macroscopic behavior. In essence, the results of quantum and classical mechanics should correspond to each other for larger masses or energy. Okay, so this is the correspondence principle that was proposed by Niels Bohr. Okay, so more about it later, but you should always take into account that historically quantum mechanics developed from Max Planck, and then it's percolated, and now we have the Schrödinger's wave equation. And we will see now that what we can do with the Schrödinger's wave equation when we start looking at the internal energy modes right now. The translational mode, as we saw, are minuscule. The energies are minuscule. So the discretization, validation really comes from the internal energy modes. Okay. Now to a mode, so we have to apply now the quantum mechanics to more complicated system, basically to a more complicated two-particle system. And that sets the stage for the analysis. And we will just look at the analysis in just a little bit. So two-particle system, and we are going to therefore use this to look at the internal energy modes, which we say it exists. This is the modes that the atoms, the molecules has due to vibration, rotation, and stuff like that. So these are the internal energy modes. So we already found recall that we already analyzed the external modes. Okay? Our translational energy modes. And that we did it by a single particle system. Translational modes. All right. Okay. So let's go to a fresh page and write the Schrödinger's equation. So Schrödinger wave equation. For two-particle system, right? So it can be, for example, any two particles. Okay, like two nuclei, proton, electron, so on and so forth. Any two particle system, right? So let's write first the energy, which is H, basically the total energy. Okay. For a single particle system, remember we said that the potential energy was 0. Okay. So in this case, of course, it is not. It's p squared by 2 m1 p2 squared by 2 m2 plus v12. This is the potential okay, for two particle system. All right, and these are nothing but the linear momentums. Momentum. Okay. So what we do next? So we know the total energy. Now we write down what we call the steady state version of the Schrodinger's wave equation. This is equation. Okay. So recall how we did the wave equation for multi-particle system. 2m1, 2 first operator, h squared bar by 2m2. Same one can be equal to m2 also, depending on what particle system you are dealing with, plus v12 minus equal to 0. Okay. So v12, as we said, is a potential for a two-particle system. So this is the steady state version of the wave equation. So what we need to do next is that we separate okay, the internal and external modes by converting to a center of mass coordinate system. Okay, so the internal motion, therefore, once you do this, the internal motion okay, can be viewed as a relative motion, of one particle with respect to another particle. Right? So you are sitting on the center of mass right now and you are watching the motion. So as a result of that, the internal motion can be viewed as a relative motion with respect to another particle. Okay. So if we now draw coordinate axis like this, see how well I can draw. So this is X, this is Y, and this is Z. Okay. So this is say M1, this is say M2, and okay, then of course let's just put it in a different color now. This is the center of mass. So this is your R1. This is your R2. This is your into R. This is mass M1, M2, and okay. So this particular, so if I join this particular branch is how the center of mass is located. It is M2 by plus M2 into R, R being the total distance. This is this part. This part is therefore written as M1 by M1 plus M2 into R. Right? So that is the other part. So this total distance in R. All right. I think that part is now understood at what it is. So motion of any particle, any two particle system can be described by the Cm. So motion any two particle system can be described by the Cm, nothing but the center of mass. So R1 is basically equal to R minus M2 by M1 plus M2 into R. R2 to R plus M1 divided by M1 plus M2 into R. Right. Therefore, P1 square by 2M1 P2 square by 2M2 is given as, because M1 by 2 into R1 dot into R1 dot plus M2 by 2 dot into R2 dot, which is equal to therefore M1 plus M2 by 2 to R dot divided by R dot plus mu by 2 equal to small r dot to small r dot, where mu is equal to M1 into M2 divided by M1 plus M2, which is basically nothing but the reduced. This is all very classical mechanics that you already know. Okay? And M1 plus M2, we can write it as MT. So the Schrodinger's wave equation therefore becomes, this equation becomes minus h r square into 2mt to the operator with respect to r minus h bar square with respect to the reduced mass, and this is square into psi plus v12 minus the energy into psi is equal to 0. So this is, implication is that the total mass is placed at Cm. The reduced mass okay, is moving relative to Cm. Okay, all right. So this is the total, this is how the separation happens. So if you look at it, this is how this was done. Two masses, so you place the center of mass concept over here, and then just working out through plain and simple math that we have already done numerous times. These are all dots that we have done. This is the key concept, reduced mass, which we already know, and this is the total mass. That is why it is written as mt, total mass. Okay? So the steady state version of the wave equation becomes this. Okay? Remember, V12 is once again the potential. Okay? And so the total mass is placed at the center of mass, and the reduced mass is moving with relative to Cm. These are the two natural outcomes that you have of this particular analysis, right? Also, please note that V12 is a function of Fr only. Okay. Okay. If this is independent particles, okay, unaffected, affected by other molecules. So this is basically the potential energy. Okay. So now what we need to do is we need to separate the external and the internal mode. Separation of internal and external energy modes, which we are going to do in the next class, that how the separation can happen, because this is what is going to lead us to a complete analysis of how the internal modes actually evolve, right? So that's why we did all this groundwork, and we also defined that V12 is only a function of R for independent particles. This is unaffected by the other molecules in the system, right? So in the next class, what we are going to see that how this separation can happen using these tools, using this form that we developed right here, using this form that we developed right here, how the separation of the internal and the external energy modes will happen. So that we will going to cover in the next class, which will be your lecture number 20. What is this?